I will speak about linked data. And linked data because it's a relatively hot topic of research. The community on the web of data and linked open data, which also called web of data, has spent a lot of time working on standards about publishing, about creating, publishing, cleansing, querying, and so on, even interlinking of linked data set. And now it's time to pass it to the next step, which is mining of this amount of data that is ever increasing. So my point today is to show you what the challenges are, and to show what the possible solution could be. Actually, what I will be presenting today are two different studies on data that actually predates the linked data, the web of data, and I'll show how this can be applied to what's now the web of data. So the first one is comparable to clickstream analysis, and it was designed for semantic application. It has as input a sequence of clicks, which may be interpreted in the linked data context, requests, URIs of linked data resources, and it outputs patterns that combine schema elements for linked data. That means classes and properties. Well, by the way, I had to announce that I am particularly grateful to Fabien, who introduced the notions from the linked data framework. I'll nevertheless make a very small recall of the very basic ones. So if you didn't assist to Fabien talk, don't panic. I'll explain what I mean by this, but right now I have to nevertheless use these notions to make myself understood. Then a second approach is a little bit different, because I'll look at linked data no more as a graph, but as some kind of structured data that fits in a tabular format. You can think of relational database. It's easy because most of the data on the web of data actually comes from relational databases, so it's a relatively regular structure to a point. So it can be imagined to be put back in this tabular format. Not that I want to have a relational database, but I apply something called formal concept analysis and mining for concept patterns to this kind of data. So in this format, graphs will be simplified into triples. I hope you remember what triples are. And then I'll show how to use some constructs to simplify, to put links from the data into more propositional, that means object attribute value type, where the values are not resources but are literals. And we'll provide then a method for extracting conceptual patterns, so concepts made of resources and their descriptions, okay, between data. So, outline of the talk. First, starting with some crash course on pattern mining, because I was speaking about finding patterns in the data. And the first topic will be frequent patterns. Then I'll speak about concept analysis and introduce formal concept analysis as an approach for pattern mining. Then this promised recall of what the web of data is. And then the two approaches I mentioned just previously. So what's data mining? Mining is the activity of finding knowledge chunks. Sorry if I'm massacring here a well-known definition, but I just need to give only the essence. So finding knowledge chunks in a large volume of data, and these chunks can come in various flavors. They can be concepts, they can be trends, they can be associations, and so on. Most importantly, these chunks, for being variable, need to be previously unknown, that means new, non-trivial, and potentially interesting. Potentially useful, sorry. Data mining is an established discipline with a large community thriving, with many venues and a large literature. So I won't be doing here an introduction of the whole domain. I only focus with what I'm interested in. This is pattern mining. But I need to say where pattern mining stands. So you can have this duality in data mining tasks, which are roughly divided into predictive ones and descriptive ones. I'm only interested here in descriptive and, as I said, on pattern mining. But if you want an example of what prediction is, this is typically classification, so in the decision tree induction. For example, clustering is another kind of descriptive technique. So to summarize, descriptive techniques will look for trends and regularities in the data without a particular question in mind, without a particular concrete variable to target them. Whereas predictive methods will answer a specific question and predict the values of a variable. So pattern mining, so patterns can be characterized as structural regularities in data records. One particular case of application of pattern mining is recommendation. So I guess everybody has already been on IMDb or in Amazon. Both of these sites will perform recommendation. And at least in the past, it used to be simple. That means based on frequent pattern mining, results from frequent pattern mining, one would find first the patterns in user consumption, and then you'll use these patterns to recommend new, previously, let's say, non-consumed products or non-visioned movies. So patterns can be maybe of different structural complexity. Simple patterns are just sets, as I show in a next slide. But there can be more complexity in a structure, like having sequences, and even more complex, like trees, acyclic graphs, or just general graphs. So what I'm interested in is the most simple for the time being. These are item set patterns. Item sets. In the framework of item set mining, patterns are subsets of a larger set of items. Items stand here for products, typically for products that are bought by a client. And the patterns themselves are also sets. Both sets of item sets are further referred to them as item sets. Exactly. So item sets as patterns, when they're mined, are filtered, because we are not interested in all potential patterns, but all existing patterns, but only by those who are potentially interesting. So the interestingness is measured by a function which tries to predict their potential usefulness, and typically we will use the frequency of occurring of the patterns as an interestingness measure. So it's called also support of the patterns. So most frequently mean will be equivalent here to most interesting. I have an example here which is not from it's not movies and neither products to buy on Amazon, but rather on the touristic side, the travel side. This is made of users who are actually named here because I'll use the same data set later on. But in typical outfit of pattern mining, actually users are anonymous. So here my users have visited attractions, touristic attractions. You can think of TripAdvisor or any other site where this visits can be tracked, part of the user profile. So the task here, we need to mine for frequency. For frequency computation, we need specific level That will be the cut level for interesting patterns. If the frequency is sufficient, that is above a given threshold, then we'll declare the patterns to be interesting. In my example, if I take a very naive 50% value, half, I can see that only 3 patterns, all of them singleton, will score above the threshold of 50%. If I lower it to 40%, then I have more. I have 8 patterns. Okay, they are there. For example, we have 2 people who have visited British Museum and Stonehenge. I guess I can use this. The British Museum in Stonehenge, the scorer and Ed. So now, to go a step further, patterns can be split, or different kind of patterns can be associations in which item sets actually are combined in a implication-like manner, where a premise item set and a consequence item set are combined. And I put here some of the most interesting associations, meaning that if somebody has visited Niagara, the same person has also visited in 100% of the cases the Louvre Museum in Paris. However, the reverse is not true. That means only 2/3 of the people who visited Louvre also went to Niagara Falls. So, how does one mine frequent item sets? The most, arguably the most popular approach is what's called Generality Test, which means that potentially interesting patterns are examined stepwise and iteratively. So the search starts with individual patterns, much like what we've seen previously, and then the size of examined patterns is increased from 2, 3, 4, and so on. And it ends whenever we don't see any frequent pattern anymore. Well, with each iteration, after the first, the result for the previous iteration is used to generate candidates, then to test these candidates against the data set of what's called transactions, I forget to say that, and frequent patterns, those occurring sufficiently frequently, are kept, whereas the infrequent are discarded. The typical algorithm for that is the Apriori algorithm, which this year celebrates years. And I show here with this diagram, sorry, no animation here, how the algorithm works. It starts by the most general patterns, which are the singletons, and goes down up till no more potentially interesting patterns are found. So in the first step, we see here this very schematic example of 5 items, each of the items examined. And since the item C is declared as infrequent, it's skipped, and everything that has an infrequent subset is no more considered. So this is a kind of monotony here, which means a item set having an infrequent subset has no chances of being frequent, which is quite logical. Yeah. So all these patterns that have no particular signs around them actually won't be tested at all. So how does this generalizes sorts of patterns? Here I provide a table which summarizes the different elements of pattern mining problem depending on the structure of the pattern of the data. Data records. I actually use the 2 extremes, the most simple one and the most complex one. Although, as we shall see, linked data is still different here. So, whenever we have to define a new task of pattern mining, we need to define a data language, a pattern language, a matching that says whether a pattern represents a data record, a transaction, a generality relation between patterns that structures the set of patterns much in the way you have seen previously, with all subsets of a pattern universe. Interlinked measure and what's called refinement operator. What are refinement operators here? These are actually the individual steps that an algorithm will use to move in the pattern space being all the possible patterns, that means the pattern language, combined with the generality relation. So what we've seen previously was a hierarchy, which is actually called lattice, because it satisfies strong structural constraints. And this lattice represents the pattern space. The algorithm will then move down using a strategy that is level-wise, and going from level 1, level 2, level 3. Okay? So, if I have the answers of any of these questions, what are the pattern language, what is the data language, what is the pattern language, matching, and so on, I can define a problem. And if I have all the necessary primitives, like especially refinement operators on patterns, I can also design an effective method. So for graphs, things get more complex. First, the languages, the respective languages are made of graphs, and you know that graphs are hard to mine because of the following problem: matching between a pattern, a graph pattern, and a graph data record is akin to subgraph isomorphism, which is a very complex problem. It's knowingly bounding. The same goes for generality. Actually, there is no surprise here because both matching and generality have the same, usually have the same nature. Now, interestingness measure, that's where I'm going, similar to the one used by Itemsets, but then there can be other additional criteria for discarding potential patterns. Now, going to refinement operators, for Itemsets, what we saw actually implicit in the strategy of the Apriori algorithm is that every time we move from one level in my lattice to the next one, to one existing pattern, we added one new item. For graphs, it goes similarly, but here we don't have items, not in the classical sense. So the operators are either adding a vertex or adding a new edge. So as I said, to define a new method, these primitives need to be combined. So first, we need an implementation for all the primitives, definitions for the languages, and we need a concrete, effective traversal strategy for the induced pattern space. That's what I'll be showing in my next the next part of this talk. Before that, I'll briefly introduce formal concept analysis, which is the techniques I'll be applying to my structural patterns. So formal concept analysis is mathematically grounded theory, or let's say framework, for about how concept will arise in a context. So these are not general concepts, but contextual concepts which are extracted from data. So this is rooted in lattice theory. This is the second time I speak about lattices, but I won't provide here formal definition because it takes too much time. So I assume you've heard already about lattices, in particular Boolean lattices. So this, so formal concept analysis has also some influences from philosophy, AI, database theory, and so on, but basically it's lattice theory. It has been, why I'm speaking about this, it has been successfully applied as a framework for pattern mining, not necessarily the plain patterns, but some particular flavors of patterns that I'm not discussing here today. There is a large literature about that. So, before explaining how the data will be analyzed, let me make some gymnastics with recoding my data. That this was the original transaction format of the data, easily be put into a bipartite graph. Okay, and you may see here that I also put some mnemonics for my long name of real attractions, so that I can spare space. By doing this, you excuse me for that compact encoding, but as you will see a real lattice structure made by formal concept analysis, you will appreciate the compactness. So my target data format is what's called the cross table, or in this particular area, formal context. Formal context have rows and columns. Rows are interpreted as objects and columns as attributes of these objects. And x's, of course, mean that a row, an object on the row, has the attribute on the column. So with that in mind, we can extract formal concepts, which are bisets, means that they're composed of one set of rows called extent and another set of columns called intent. So formal concepts can be thought of as being a bicyclics, maximal bicyclics of the bipartite graph that I've just shown you. Another way to see them as a maximal non-contiguous rectangle in the data represented as a formal context. For example, I have the concept 2 here. You see here all the concepts from the formal context, which are organized by generality. You can recognize some of the patterns I previously showed, although these names are coded here, and this is different to see. But let's say in the context, in the concept 2, the intent is made of Louvre and Niagara Falls. It's just mentioned before, it was of support 40%, and indeed we have the extent, which is made of Anne, who really visited Louvre and Niagara Falls, and Ben, who did the same thing. The intent is not made of all the visits, but just by the shared visits. Okay, and it is a kind of pattern as well. So why concepts are more interesting than plain patterns? Because we can interpret them, for recommendation purposes at least, we can interpret them as user profiles with the shared visits and the users being grouped together. And recommendation, one can think of using non-shared visits. For example, one can see that Anne has also visited Ben also visited the Lascaux cave. One can think of suggesting to Anne what actually she missed from the Ben's visit, because they share a common profile here. So this is a way of seeing that, although it has some limitations that I will be discussing later on. So now let me move to the goal of Web of Data basics. So we have graph structure in which resources, which are drawn here in red, okay, are connected by properties, which are the edges. Properties are, so I said properties, links of properties. Properties can connect also resources to literals, which are drawn in dark blue rectangles. Here I have two people who have visited Montreal. Oh, sorry, one of them has visited Montreal, and the other one has visited Beijing. Okay? Montreal is connected to Canada, the representation of Canada. And we have indications of the population. We have the names here of the two tourists who all of this are literals. So usually both resources, entities, and links or properties identified by URIs. Here you have the qualified URIs, meaning that I don't see here the exact URI, but one that is replaced by a prefix to make it more compact and human friendly. We have also indication of the type of this two resources, which is person, and it comes from a specific vocabulary for different resource types, which has been mentioned by Fabien last Friday, which is FOF. DBpedia is another one, vocabulary, very popular, on the web of data, and we use it to define the types, actually to import the definitions of entities that are widely recognized, so the cities and the countries. So we, with such a data, which is a graph with multiple sorts of links, also schemas. In schemas, schemas define the way properties are connected to types or classes. So each property has a domain type, which is a resource type or class, and a range type, which can be also a resource type or a simple value type. Here, the name of a person is a string, but the value of the visited property is a resource type of, from Wikipedia called city. So before I go further, I just must remind you that besides connection between properties and resource types or simple data types, there are also generality links between either classes or properties, object types or link types, expressed as RDFS subclass of or RDFS subproperty of, which actually come from the standard vocabulary of the RDFS language. RDFS is the language to describe linked data schemas. By now, this is a challenge. Why linked data challenge? I spoke about graphs, and indeed there are a large literature on mining graphs. Yet, the graphs that are known and well mastered in the data mining literature are of, I would say, lesser structural complexity. In particular, because they usually use only one type of links, so it makes for a single dimension of the structure, whereas in linked data, we'll mix different kinds of links, and it makes for multidimensional. There are still, I would say, there are some recent works on mining types of data that start approaching the structural complexity of linked data, but we are not there yet. In particular, one important element is the availability of a schema. So they usually rely too much in data mining area. One would rely too much on a schema that is actually constraining the graph, although the schema that we have in linked data are not constrained. They are just used for inference, but they don't provide really constraints. That means, since we have an open world semantics, at any point, new links can be added to between two resources, and then they don't need to belong to the schema. That's just everybody can say anything on the web of data. So another problem that may come here is that the web of data is in constant evolution. So it puts the emphasis on the design of online methods, which are more complex to achieve. And of course, I need to say that big data is here. I'm not speaking particularly about that, but James, was correct about that. Linked data is considered as one of the possible formats of big data, since it's graph and it's very rich structure. And most of all, of course, there are now a huge amount of data published on the web. So it's big data. Okay, so I'm done with all the introductions, and I can go straight to what I had to propose today for you. So first, my point will be to convince you that it's important to observe, to put the links into the pattern language. So I'll use the same kind of example, which is tourism with users say connected to resources of e-tourism type. But this, in this particular outfit, I won't insist too much on users. I will insist on them in the second part, in the second approach I would discuss today. The first one, emphasis is only on e-tourism objects, and I have a large variety of them. So instead of just having attractions, I add to the landscape destinations, accommodations, and I can go further on, but I think it's enough. So there is a real hierarchy here. I have the class destination, which is split into subclasses country and urban area, which itself has subclass travel, city. All these come from a particular vocabulary called travel, which is completely, or TRAV, which is completely invented here. Then accommodations can be hotels. It can be something else also, but I skip here the details. And hotels can also have a subclass luxury hotel. Then attractions can be museums or monuments or, yeah, you name it. Different properties I used. Destinations have accommodations, and they have also attractions. Then, in somehow predictable manner, a subproperty of has accommodation is a has hotel. By the way, you can often see this kind of naming conventions on the web of data where the property just adds has to the name of the range class. So has hotel because the range is hotel. Okay? And has museum is another property which is a subproperty of has attraction. Okay? Is everything clear? Okay, because now it starts getting more interactive. And I have other questions for you. So since I'm interested in recommendation, but I'll put everything in a more dynamic context, I propose with the following exercise. Let's say again we with our previously introduced users Anne, Ben, Cora, and so on. And I have registered only 3 user sessions with semantic, let's say semantic portal, where people will actually click on web pages corresponding to resources and try to compose something like itinerary for their next visits. I mean global visits, going somewhere to travel, sorry. Okay, and let's assume that we have first transcript of a session where Anne, whatever the technology behind, to guess what she did, first click on Germany. Oh, sorry, this German is Y is disappeared, vanished here. I don't know why. So then she clicked on a page representing Dresden or requested something about Dresden, Berlin. Then a hotel add-on. I can tell you that this hotel is in Berlin for disambiguization purposes. And finally, or let's say till this goes, till my example goes, she clicked on the Pergamon Museum. For those of you who don't know, this is a famous museum in Berlin. Then Ben did similar things, not exactly the same, but for United Kingdom, he clicked on London, then on Sofitel, Covent Garden Hotel, British Museum. Then somebody came to Montreal, wow, and clicked, of course, first on Canada, Toronto, Montreal, probably hesitated which one of the city, then Ritz-Carlton in Fine Arts, Museum of Montreal. So let's think now we have an unfolding session where our Dan has clicked on France, then Paris, Ritz, and stopped. And we want to help him go further. So my question is, what do you think the right suggestion, the right recommendation will be here? I mean, it's obvious, but still. Yeah? Louvre. Yeah. Very well. I mean, if you understood that, I probably can stop here with this example. I know, not only the example, but the whole approach. Because, you know, you correctly guessed that just because you saw a pattern in the user sessions. Okay? And I'm sorry about that. This was a nice surprise, but my animation didn't work. So let's try to make it a surprise nevertheless. Okay, so you probably think that you guessed correctly because you saw that somebody first clicks on a page of representing a country, then goes to a relatively big city, finds a luxury hotel before thinking about something more cultural, and finds a nice museum to see when you're there for the first time. Well, the question that I actually spoiled was, okay, do you think that in such a schema there is enough information? And the question, of course, is a trap, because if I only have this, it's not enough. Why is not this information enough for a computer to use the pattern as a recommendation basis? Because I could actually suggest as well British Museum. Because British Museum is just a museum, okay? But now, if I have a way to constrain my classes here that are actually shown, which you were the one who abstracted from my user sessions, if I can put some constraints saying, okay, first the city must be in the country that has been visited. Then the hotel must be here. And also the museum must also be located in the city. Okay? Everybody agrees with that? So my point now is how I mine such patterns. How I go from my initial sessions, and it's even worse than that, we shall see that in a second, to these nice patterns. So I'd say the challenging mining problem. First, there are some definitions to make, and then, of course, we need algorithms that efficiently mine that kinds of patterns. Okay? So I must disappoint you. I don't speak about algorithms at all today. Just because I decided not to put any formula on my slides. For those who know me, this is surprising because I usually put lots of formulas. It helps me. Now it's a bit more challenging, but I hope I'll be up to the challenge. So first, define the data. The data is not going in the right format, which is actually this one that can help the abstractions and abstraction of interesting patterns. It actually originally looks like that. These are just requests for some URLs that are stored in the web server logs and registers user sessions with our semantic portal. Then this can easily be translated as requests for particular resources, but still we need our constraints, okay? Because these are, the links here are the support for mining the previously mentioned, oops, sorry. Okay, let's look here then. This is my pattern language. I'm doing that one-step look. So to have this nice constraints here that represent the properties from the schema, we'll need to have these links imported from the link data. So just, yeah, again, what step? No, I'll go to the right place to say that. So if I imagine this, sounds without surprise, my pattern language, the elements of my pattern language, the patterns, then I have to warn you that you don't need to think of them and also of the previous format as being the resources themselves. These are requests for resources rather than resources, because if I start constructing something like that, and if I want to exchange that for somebody with somebody else, even why not publish on the web, then I'm in a big trouble, okay? Because I'm saying things that are not necessarily always true, okay? And especially that I have to have sometimes repeating mentions of the same class or even of the same resource. So these are not the resources themselves. These are kind of placeholders, or if you want, these are surrogates for them. Okay, so I'm going speedier because I have a time problem. I was very low to start. Patterns must be matched to data records in order to estimate their interestingness, their frequency. I will be going here with the frequency, the most basic one. So matching here is a very interesting problem. I'll be back to that in my conclusion part if I go to them. But one of the principles, not that I have a nice algorithm, not yet, doing that very efficiently, but at least I have the mathematical formulation. Excuse me, there are strong maths here, or at least some interesting maths, but I hide them so you don't see them. So the way I put it is, if I want to know whether a pattern is a summary of a particular data record, I have to find a mapping from any element in the pattern to an element, distinct element of the sequence of the data sequence that respects the order. So the images of two class elements from here should be in the same order in the sequence. And moreover, there needs to be compatibility of types. That means, for example, Montreal needs to be a city. It cannot be a Luxor hotel if it's associated to this class element. Okay? Does everybody understand what happens? There are also some other constraints. So the properties need to be mapped to links that are also either links of the same property or of a subproperty of them. For example, has attraction has been mapped here to has museum, but has museum is just a subproperty of has attraction. Okay? So put in this way, it's easy to say, but mathematically it needs some definition. Anyway, you just need a flavor of that. The same goes with the generality. I have almost the same constraints to respect. Only here I map class elements to other class elements which are compatible. So a class mentioned here needs to be a superclass, or identical class to the one that it's mapped to. By the way, you understood that this is the more general and this is the more specific pattern here. So it goes this way. Now, the more interesting question is about the structure of the pattern space. How do we move from one pattern to the patterns that are immediately below? Remember that in the large lattice of all item sets, it was easy. We had to add one new item. But there is, as I said previously, no item here. So what are we doing? Well, we have some operations. Some operations that can be used nevertheless. And without any surprise, because Jim is starting to press me, there are four actually refinement operators, which are akin to what I mentioned about graphs, between adding one edge, adding one vertex. Here I have the adding part, so adding one new vertex in what's kind of a graph here, actually sequence that's completed to a graph. So adding anywhere one new, but you see root class. Not any class can be added at any point, but root class. Then I can add also one root property, but more interestingly, using the hierarchies of subproperties and subclasses, I can replace an existing class by an immediate subclass, or existing property here by an immediate subproperty. So with these four operators, I have the structure of the pattern space. So I'm speeding up. Obviously, have to skip the second part of my approach part of the talk. Just to say that even defining here what a level in the pattern space is tricky, because patterns of similar structural complexity actually can be of very different levels of generality. This one is probably one of the most general, and this one, which is isomorphic here, is much more specific. Okay, so I take 2 minutes to summarize what I had to say. Well, you have 20 slides to follow, actually not much. But to move back to formal concept analysis that I introduced and explain how it can be extended to match, to perform analysis of linked data. Okay? It's not that I'll put graphs directly, but I will code graphs. Right? This is the motivation that's not important. Code graphs into a way that is, into a format that is compatible with formal concept analysis. And we have a different schema here that, again, users against attractions and visits of these attractions. So I'm back to my duality, only users and attractions, with part of the graph represented here, with additional properties that help define, actually, finer similarities between user profiles than just matching, exactly matching visits, subsets of visits. This is the way it can code it, and I have the property visits, which deserved coding of its own, plus all other properties of the respective types being encoded in formal context. So with that in mind, I actually end up, and I'll skip here all the explanation how this is structured into lattices, because the two contexts are easy to, and I finish my talk here. To encode links, this time we don't use graph structure, but specific constructs that I actually borrowed from description logic. And description logic, as you may know, uses this way to actually bring first-order information to propositional ones. Okay, we have propositional items that are composed in a way you can understand probably that if I say that Dan is a user and he visited Lascaux, I can say that, knowing that Lascaux and Mont Saint-Michel are French attractions, that Dan has visited at least one French attraction. And actually, since these are all the known visits, all of his visits are French attractions. Okay? The trick here is I don't have the French attractions class, but, well, guess I can find it. I can find it and then use, not that I can name necessarily French attractions immediately, not that the machine can recognize it, but the machine can discover concepts and use them instead of this nice named classes to produce automatically new items or formal attributes, as you can see here. And then if I add the new attributes to the existing ones, I go to a larger lattice when some new groupings and new concepts will arise on top of what already has been produced with the initial codings. Okay, I'm done. I just conclude that links, as you might see here, are very important. They provide context to resources, and taking them into account, mine them in a mindful fashion is important. So I show two ways of doing that, and I am particularly sensitive to the context effect. And this is how this context effect played out in my two approaches. So I think I stop here. Otherwise, I will get killed by James.